Many thanks to the organizers for bringing us together for this beautiful conference. As mentioned, I'm going to talk about machine learning for improving one particular step in many amplitude calculations, namely the integration by part reduction of Feynman integrals. This talk is going to be based on work together with Matt von Hippel that we put on the archive in February. But this was the first paper on the topic. It hasn't remained the last one. And 4 days after our paper appeared, there was another paper by Song, Yang, Tao, Lu, and Zhu, at least one of them being in the audience. And then in April, there was another paper on the topic by Mao Zheng, who is also in the audience. And I would strongly suggest that you check those papers out as well. Moreover, I plan to mention some work in progress together with Justin Behrman, who is also in the audience, and François Charton. After giving you a short introduction, I will first tell you what integration by part reduction is. Then I'll introduce two machine learning approaches we can apply to improve it before wrapping up and discussing some perspectives. During the last years, machine learning has transformed many aspects of science and society. In particular, with the introduction of ChatGPT, it has been also becoming very prominent in our everyday life. Machine learning typically excels in situations where we have noisy and numeric real-world data. In amplitudes, we usually have exact and analytic calculations. So that doesn't sound like an ideal match. However, in amplitudes, we also have many situations where it is hard to calculate something, but quite easy to check it. I want to argue that in these settings, we do have a case for machine learning. If the machine is able to learn to give us a guess, we can easily check whether it's correct to have a solution that we can trust. During the last years, a number of these situations have been investigated. The first is the symbol bootstrap, already mentioned in Ruth's talk. And there, François gave a beautiful, as I was told, I couldn't be there in person, talk at last year's Amplitudes. So for the bootstrap, we have infinitely many constraints. So if we get a machine to give us a candidate solution, we can easily check whether it's correct. A second example is the simplification of spin helicity expressions. This challenge is as old as the Park-Taylor amplitude, which Ruth also showed on the slides in the previous talk. And if you have a spin helicity expression and you want to simplify it using Schouten identities and momentum conservation, it's actually quite hard. But if somebody hands you a solution, you can simply plug in integer values for the kinematics and check that it agrees with your original expression to infinite accuracy. And Matt Schwartz already gave a very inspirational machine learning talk at the Amplitudes conference 2 years ago in Prague. The third example of this is integration by part reductions. And this is the topic of my talk today. The traditional pipeline for calculating amplitudes for precision predictions at the LHC or for gravitational wave observatories looks as shown here. We are starting with some Feynman rules, getting Feynman diagrams, expressing them in terms of scalar Feynman integrals. And in state-of-the-art applications, we arrive at hundreds of thousands of those Feynman integrals. They are then reduced via integration by part reduction to master integrals. And typically, there's in the order of hundreds of those. Then we calculate the master integrals via differential equations, where we again need IBP reduction. before combining master integrals and coefficients to get amplitudes. Of course, there's been many improvements to this pipeline over the years, in particular from within the amplitude community, and Ruth has given us a very interesting overview of those already. In particular, there's many techniques to get rid of Feynman diagrams, and we'll hear more about those in talks by Jake, Yara, and Song. And in some situations already mentioned by Ruth, we can even bootstrap the whole result, thus circumventing this whole pipeline by making an ansatz for the final result. And there will be talks about this by Lenz and Qing-Lin. But in many Pheno applications, IBP reduction still remains the major bottleneck. For example, in this for loop calculation in gravity from last year, IBP reduction alone took 300,000 CPU hours of compute. But what is integration by part reduction? Feynman integrals form a vector space, and the dimension of this vector space is guaranteed to be finite. We can thus pick a basis, and we call the basis elements master integrals. IBP reduction is then the step of decomposing any given integral as a linear combination in this basis. By now, a number of public codes implement IBP reduction, such as Air, Fire, Reduce, Light-Red, Kira, Finite Flow, and Blade. There have also been improvements that either simplify the IBP reduction by picking particular synergy improved IBP vectors, synergy improved IBP vectors, and those are available now as neat IBP. And there have been ways like intersection theory aiming to get rid of IBP identities altogether. We'll hear more about intersection theory in Pierre Paulo's talk later this week, but it hasn't produced general purpose codes yet. But how does IBP reduction work? To tell you about this, we need to first look at a general family of Feynman integrals. So we are looking at L-loop integrals, and we are indexing members of this family by integers a1 to an. The integral is over L loop momenta k in d-dimensional Minkowski space, and the integrand contains these polynomials di in the loop momenta. They arise to powers ai, and if ai is positive, this is a propagator. If ai is negative, it's an irreducible scalar product in the numerator. Now, IBP identities arise because the total derivative, the integral of a total derivative vanishes. On the other hand, if we are contracting this with an IBP vector q, then this becomes a scalar, and we can express it as a linear combination of members of this family of integrals, where by applying the chain rule here, the indices can be shifted by plus minus 1. These integration by part identities cannot be solved in the general case for generic values for the AI. So what we do instead is to specify particular sets of tuples of integers ai called the seeds, and then solve it via Laporta's algorithm. And this step, the seeding, is what I'm trying to improve with the IBP, with the machine learning techniques. Now, this was all very abstract, so let's look at a very concrete example, the example of the one-loop bubble integral. Here we have two propagators, one with a mass m, the other one massless. And we have two indices, A1 and A2, which arise as the exponents of these two propagators. Moreover, P is the momentum flowing through here. The IBP identities in this case can be calculated quite easily from the general formula here by inserting Q to be either P or K. And this is a very quick calculation that I've given my students in quantum field theory as homework many years in a row. Now, if you want to seed this, or first mention master integrals, here there's two master integrals. And you can pick those to be a 1, 1 and a I, 2, 0. Now, say we want to reduce I to 1. If you want to see this one here, I can tell you that the easy solution is to pick the values A1 and A2 equals 1. So if you insert those into those equations and you take the difference, those two terms drop out. And then you can indeed express I2, 1 in terms of I1, 1 and I2, 0 with this expression. But what if I ask you to reduce I5, 5? What values of A1 and A2 would you then put into these equations to connect it to the master integrals 1, 1 and 2, 0? In general, the best answer I have for this is heuristics. And to describe the heuristics, we need to introduce some notation. So for such a tuple of integers, T counts the number of positive AI. R is the number of the sum of positive AI. D is the difference between R and T. So this is the number of dots or propagator repetitions. Then S is the negative sum of negative AI. So this is the total power of these loop momenta in the numerator. A first heuristic is then a rectangular seeding strategy, which tells you to pick all tuples of AI for which R is bigger than a particular maximum parameter, smaller than a particular maximum parameter, and also S is smaller or equal to a particular maximum parameter. The golden rule of Laporta is then a refinement of this rectangular seeding, where additionally we require that D is smaller or equal to a third parameter D max. So in the homework I gave you on the last slide of reducing I55, Laporta would then tell you to plug into the equations all values of A1 and A2, which sum to less than or equal to 9. 23 years after Laporta, in a talk at QCD Meets Gravity in December 2023, Johan Usovic proposed another heuristic, which is now called improved seeding. In addition to the golden rule, he requires that S should be smaller or equal than T minus L plus 1, where L is another parameter. Now, this sounds like a very small change, but it actually has a huge impact on the performance. It leads to an order of magnitude drop in the number of seeds, and thus in the time it takes to do this IBP reduction. Now, when I heard this talk, I thought we could either wait for another decade for someone to come along who has an excellent understanding of this IBP reduction to come up with a better heuristics, or we ask machine learning to come up with a better heuristics for us. And to recall, this heuristics is about finding this small set of seeds small set of equations in this big set of linear equations that we need to solve. We always use this particular two-loop integral for benchmarking our machine learning algorithm here. And this was also used by Johan in his talk. And it's got a bit more structure, a bit more realistic terms of complexity than the one-loop bubble integral. So let's now apply a first machine learning algorithm here. Oh, sorry, I'm running a bit late. So it's called FunSearch, and it's coming from a Nature paper from Google DeepMind in December 2023. And if you want to describe it in just one line, it would be solving problems by automated brainstorming using the combined knowledge of the internet. You could describe it as asking ChatGPT to give you a solution to your problem. But being programmed the way or trained the way it is, ChatGPT surely will oblige. But since it doesn't actually know what your problem is or how to solve it, you should better ask it to give a Python code so you can check how good the solution to your problem actually is. And if you've got a couple of good solutions, then you can ask ChatGPT to approve on them to start a loop. Now, in the words of the authors, ChatGPT works by using a pre-trained large language model. And here the authors, being from Google, used Google's code completion model, CODI. And based on a prompt, this designs new programs which you can evaluate. And the best ones are put into a pool of programs from which you, again, then choose two to prompt for an improvement. This is a variant of genetic programming which aims to mimic biological evolution and survival of the fittest by here taking the large language model to do the crossover and mutation steps of evolution. Moreover, the output of this is Python code, making it interpretable and thus also generalizable. Since we are talking about survival of the fittest, we need to talk about what we mean by the fitness of a seeding strategy. Gauss elimination algorithm, which is used to solve these linear equations, scales cubically in the number of equations and the number of unknowns. So less seeds is better for runtime and also memory. So we define the fitness to be minus the number of seeds, but only if those seeds suffice to solve for all of your unknowns in your original integrand in terms of the master integrals. If they're insufficient, we add an additional penalty being the size of the Laporta system. However, these equations are also sparse, so you can do a bit of refinement on this by counting the number of element-wise operations you have to do. And this was done by Mao Zhang in his paper. The starting point for this experiment was the following Python code, which implements a golden rule Laporta system with dmax equals 1. And this leads to 2,148 seeds. Now, running this for 2,400 generations, so this is order of magnitude 1 or 2 days, these seeds were reduced to 92 seeds. And those 92 seeds are actually implementing or equivalent to implementing the improved seeding strategy with dmax equals 0 and L equals 4. Thank you. So we were able to rediscover the state of the art that was introduced by Johan 1.5 years ago with FunSearch. Now, letting FunSearch run another 1,400 generations, we were able to reduce this number further to 88. And we could interpret that this was equivalent to the improved seeding strategy, with t being required to be bigger or equal to 4. So we even found a small improvement over the state of the art. Now, a second version we attempted was strongly typed genetic programming. Fun search is unconstrained and thus slow, making it well suited for exploration. What we also tried is more classical genetic programming, which is constrained in the function it can produce, but thus also much faster, potentially working well for exploitation. It works by representing a function via a syntax tree. So for example, arg1 being bigger than 0 and arg2 smaller than arg1 plus 3 can be represented by the tree with a root end, a node bigger with leaves arg1 and 0, and so on. Not every tree is a valid programming expression. So for example, 3 plus true is clearly nonsense, but this is taken care of by strongly typed genetic programming. The evolution of those trees is then essentially grafting, which is done for fruit trees as well. So we can do a crossover by replacing a randomly selected subtree of one tree by a randomly selected subtree of another tree. And we can do the mutation by replacing one randomly selected subtree of a tree by a new randomly generated tree. As building blocks, we were then using these combinations of AI. So this is the R I mentioned before, and some bigger, smaller, equal, plus, minus, and some integers and true. Now, letting this run for 18 generations, we again found 88 seeds, equivalent to the improved seeding strategy. So the same result as with fun search, but much faster. By the way, this is the final tree, and you see it takes some interpreting to break it down to this one line. So in view of time, let me wrap up. Integration by part reductions is a main bottleneck for analytic calculations of amplitudes for both LHC and gravitational wave reductions. Observations, sorry. So the challenge in improving IBP reductions is to pick a set of seeds, so picking a set of linear equations to solve. I've given you two machine learning approaches to do that. One being fun search, which uses a large language model that's pre-trained. The other being more classic, strongly typed genetic programming. In both cases, we were able to rediscover the state of the art and find a small improvement on it, thus making for a nice proof of principle for applying machine learning to the problem of IBP reduction. I also want to discuss two options for generalization to more complicated integrals and deployment. One uses the fact that Python code and the output of the strongly typed genetic programming is actually interpretable. So we can read off some analytic seeding strategy that can be deployed. One example is this lower bound on t, which we found. Another example was this elliptic seeding strategy that our Chinese friends found for the one loop integral, and where they were able to show that it generalizes in various degrees to these cuts of 5-loop bubble integrals. Another option uses the fact that many IBP codes use finite field techniques to limit the swelling of intermediate expressions. That means we are running the code, the reduction, many times for different finite field values of the dimension, the masses, and the Mandelstam variables, and then reconstructing the analytic dependence on those quantity via some Chinese remainder theorem and Thiele reconstruction. For state-of-the-art integrals, this typically gives us some 10,000, 100,000 runs we anyway have to do, during which we can improve the IBP reduction on the fly. So this gives us the option to potentially deploy also the machine learning algorithm itself together with the IBP code, which would also allow to find particular improvements that are tailored to the specific set of integrals that occur in your physical processes you're trying to calculate. So far, I've talked about fund search, which is based on a Google DeepMind publication from December 2023. And in machine learning terms, December 2023 is the Stone Age. Now, last month, there was a new announcement by Google DeepMind of AlphaEvolve. And this is scoring better or across the metrics, in particular needing much less runs to find an improved solution, which makes it very interesting also for applications to the problem of IBP reduction, and it would be very interesting to use it here. Also, so far, I've told you about strategies of picking all of your seeds, all of your equations to solve at once. Another option is to pick the seeds one by one. Now, picking equations and unknowns to solve for can be thought of as moves in a game, similar to moves in chess or Pong shown here. That means one can apply reinforcement learning. And this is what Mao did in his paper from 2 months ago. And together with Justin and Francois, we are also investigating this approach now. Apart from equation solving, machine learning could also benefit other aspects of IBP reduction. As mentioned on the last slide, we're doing these runs for many values of finite fields and then reconstructing. So this gives the machine one guess per run to come up with a rational expression. Moreover, I'm convinced that in the next years, machine learning will have a big impact on our community, also to many other problems. Thank you.